All right. So, morning, everyone. Today is the another issue with the beam, but this time we don't have enough bracing, so that we need to consider the unbraced length of the beam, which will dictate the flexural capacity of the beam. And this is the picture from the my work a few years ago. You see that we have the beam here. This is the beam. Okay. That steel beam is 12 meters long. Okay. That is 12 meters. Maybe I should use red so that you can see. 12 meters long. And as far as we're concerned, you see this beam is completely in the air. So it is free to move laterally because there's nothing to brace except, the point here where the truss is being supported by the beam. So this truss that you can see is standing on this beam. And as a result, it can help brace the beam from moving, in and out of the plane. So therefore, in considering the design of this beam, I can say that, the bending moment is from 12 meters. Okay, when you perform the structure analysis, of course, you must analyze the beam with the moment from the 12-meter span. But when we consider the resistance or the load carrying capacity, for the load carrying capacity of this beam, it is based on the unbraced length of 6 meters. So you can say the unbraced length of 6 meters. Okay, we don't consider the unbraced length equal to 12 meters. Our unbraced length will be 6 meters, and that's how we can calculate the flexural capacity of this beam. Okay, so that's the case. If you consider that this beam unbraced length is 12 meters, your beam is going to be extremely very, very big. Okay, and we can do this, and we can also consider some other factors which I'm going to mention in a few minutes. Okay, one more thing I like to talk about is that you should question about what can be considered the bracing. Okay, say in columns. Too big. Okay, what can be considered bracing? Say in compression member. What you have in compression member is the global buckling of the member, which you can say it's a lateral buckling. Okay, so if the buckling is called lateral buckling, something that can be considered a bracing is something that can stop the lateral movement of your column. Okay, so if the lateral bracing can be, the lateral movement can be stopped by some member, that member can be considered bracing. Okay, now in flexural member, when your member is not laterally sufficiently braced, we will have the behavior in the global buckling of the beam that is called lateral torsional buckling. Okay, when the beam is not like the compression member, where when you have a compression member, when you have the member, okay, the load is in your principal axis like this, right? So it causes your member to just buckle. But in flexural member, let's say this is your beam, the load is in this axis, okay? Or whether it is the uniform load or the point load. But this load, you know, it's not in the axis of the member, but it can cause your member to lose stability to the side like this and twist. So when the unbraced length becomes something that we need to consider, the behavior that follow is called lateral torsional buckling, okay, or LTB in short. So what can be considered a bracing would be something that can stop the bracing, stops either of them, of the lateral movement or a twist. Okay, so if you can prevent your beam from moving laterally, or if you can prevent your beam from twisting, you know, the distance between the members that can help prevent those things is considered the unbraced length. So I would like to mention this first because I begin with the real picture, so that in the hope that you can see the behavior. Okay, so let's come back here. You see, this point can be considered the bracing because, you know, this truss is coming down on the beam, and, you know, look at the system of the truss. This should be strong enough to prevent the movement of the beam at that particular point. So that is why this point is considered a braced point of the beam, and the unbraced length in terms of the design becomes half of the entire length of the beam, or 6 meters. Okay, this truss will act as a bracing, as you can see, because truss coming down here, and that is where the truss is connected to the beam. And look at the system of the truss. This should be more than strong enough to help prevent the movement of the beam in lateral direction, or, you know, twisting. Okay, and this is the museum that I mentioned yesterday. You can see the size of a human being there. You see how big that is. And, you know, when I believe, this is what I believe, when you do something right and you look at the size of the members, they look reasonable. You know, you can go there and you know, have your field trip if you want someday. Okay, so that's the introduction. So let's come back here to the slide. All right, so that's it. Beam that is laterally unsupported. Generally, this is mentioned earlier, that when you have the unbraced length, you know, like this, green is fine. Unbraced length, you know, the length that is between the two brace points, as I showed you earlier. Your beam may buckle, you know, under compression, because flexural member, you know, part of it is compression, part of it is tension, as we all know. And when the buckling occurs, your beam can move sideways. You know, say this is the side view. It can move from the center line here sideways. And by doing so, it cannot just move there, it has to twist as well, right? So if you look at the front view, you will see that your beam move to the side and then twist. That's why we call it lateral and torsional buckling. Okay, and if you look at the side view of the beam, you see that the beam will deflect down slightly. But the whole idea is that your beam under compression will be forced to move sideways and twist should instability become the issue of that particular beam. Okay, so you see we have two kinds of displacement involved, rotation and typical displacement in the lateral direction. So that means in considering the flexural strength of the beam when it is laterally unsupported, you need to consider two qualities. Okay, that is the stiffness of the lateral movement, but I will not go into detail because if you really want to know how you can develop the formula to approximate the behavior of the beam, that's a very advanced stuff. You need to the graduate level, so and so. Okay, and in torsion, this is the typical deflection formula that you can get from double integration or something like that, you see. But remember that our deflection is in the horizontal direction, not vertical, okay? The next one is the torsion. Now there are two kinds of torsion. Generally, if you talk about something like this is called the closed section. The section is closed as a loop, or this is closed section. The closed section is very, very good against torsion. That is why you guys started studying the torsion in mechanics of materials with this kind of shape. Okay, when you consider this, it is only pure torsion if it's a closed section. Okay. But if the section is not closed, particularly the H shape that we generally use, you see there's a part where it just stands out like this, which is a flange. So this section is by no means a closed section. It will have another behavior called warping torsion for the flange part. That means when the torsion occurs, if it's a pure torsion, your member will twist only in plane. But when, let's say, when this is your shape and say this is your plane, if your shape is not a closed loop, the torsion will not only occur in this plane, the green plane, but the torsion will also force your member or your section to be warped out of plane like that as well. So that's another issue. So there are two kinds of torsion, but that's all you need to know. So when we consider the lateral torsional buckling behavior of the beam, there will be the torsional constant and warping constant involved. So all in all, two aspects to consider the lateral torsional buckling: the lateral movement of the member, in y direction. Okay, it's not the major deflection; it's in y direction. That's why we need IY. You see, and then the twist of the section. And for the H shape, there are two kinds of twist: the pure torsion, where everything twists in the plane, and then warping torsion, where part of your cross section will be forced to be twisted out of the plane. Okay, there was a guy who came up with the critical moment that will cause this lateral torsional buckling, and the way that this was proved by mathematics never ceased to amaze me. I am still amazed by the guy who came up with the exact solution of lateral torsional buckling. So out of the world. Out of this world. Anyway, so as you have seen from this previous page, there will be the torsional constant and there will be warping constant involved. So it is these two qualities, the J and CW. J is for the pure torsion, right? And CW is for warping. You see the W. Generally, J can be calculated by the summation of sigma BT cubed over 3. and CW is basically h squared multiplied by IY over 4. I give you some short examples in case you may have to do it yourself, but for any H shape, you should know that these values are available in my engineering table. You don't need to calculate any of these as long as you use the cross section according to TIS standard. Okay, so let's go visit our table a little bit. Actually, it's in here. Right? One moment. Here, you can see if you look at this table, no, it's not in here. It's in the main table. Oops, I keep doing the wrong thing. One moment, please. No, it has to be the main table. This one, okay? In this table, it has J and CW included already. So you don't need to bother to calculate them if you need to use them. And there are two other properties that you may need to use in the calculation of the lateral torsional buckling. That is RTS and it's too small. Is that? The H naught, they are also available in this table. So whatever you do, don't lose the tables that have been given to you, okay? So that's that. But should you, oops, that's the wrong one. Right. Seems like it's not a very comfortable morning, somewhat. Okay. So, okay, we're back here. If you need to calculate J for the build-up section, for example, it's this formula. Keep in mind that B is always the width or the length of the plate, and T is always the thickness. So in this case, we have two plates for the flange. So 15 becomes a B, and the thickness, sorry. The 15, that's a width, and 1.2 is T, see, it's a cube. And for the web, you see 42.5 centimeters, it's a B term, and 0.9 is a T term. Okay, so it's that simple. All right. So now, in the general basic case, please don't be, discouraged by the formulas because it's just the basic of how things come about. But we don't need to use these formulas. And as I say, you would have this term for the pure torsion and warping torsion in the calculation of the flexural strength of the beam when lateral torsional buckling becomes the case, becomes the behavior of your beam. Okay, and that's all you need to know. All right, so the formula for that generally, is developed by the idea that, our beam is under heel bending moment. Okay, this idea that I just mentioned has been based on the fact that your beam is under pure moment. But in the real world, only one case or two cases that you can have the pure bending or constant bending moment. Okay, pure bending means constant bending moment. And this your bending moment diagram as a result is a constant like this. First is when you have the free body diagram like that, or second, when you have a free body diagram like that, but the first is more like you have the pure moment applied. The second case is when you have zero shear. Like I can write the beam like this, and if I apply force like that, your bending moment diagram will be like this. So that is when you can have the constant moment as well, right? So either you have no force applied, just pure moment, or when you have the force applied, but you encounter the case where you have zero shear. Because this case, in this beam, your shear force diagram is like this, right? So zero shear here results in constant moment here. So that means you can, the only case where we have the bending moment diagram that is a constant like this is pretty rare. And when you have the bending moment diagram that is not a constant, something like this, or say, if you run the continuous beam and you have the bending moment diagram like this, you have both positive and negative moment, or you have the moment that changes the value, your beam will become more difficult to buckle. So with that idea, before we look at the formula, you know, and start considering the hula baloo of things, we need to understand the fact that the formula that they have developed is based on the constant moment, which is not real in most of the cases in the world. So we need to consider the help from the bending moment that actually occurs on your beam as well, because whenever your beam becomes, whenever the bending moment on your beam becomes a non-constant value, your beam will be much harder to buckle. Okay, like this case, you know, okay, like this case where I just show you, if you look at this beam support the truss, correct? So let's say if I don't consider the weight of the beam, my bending moment diagram of this beam will look like that, because I have a point load, okay? And I will consider the effect from the fact that my bending moment diagram is not constant. And my unbraced length is also here as well. So my unbraced length, or LB, is 6. And then I will also consider the fact that my bending moment diagram is not constant. I consider both of that. That's why the beam doesn't look so big at all. Okay. And we consider the fact that our bending moment is not constant. You know, this is the typical case, constant moment. But when your bending moment diagram is not constant, oh, here we go. Just a moment. Okay, we're back in business. When your bending moment diagram is not constant, like this, or like this, we need to consider the help from bending moment as well. Okay, so let me write it down in letters. Typical. Beam is easy to suffer LTB. And then in some other case, whatever the case you may have, moment not constant, beam becomes much harder to suffer LTB. TB or lateral torsional buckling. Okay, and the value that we can use to evaluate the impact or the influence of the bending moment diagram that may help us increase the strength of the beam is reflected by this CB value. Okay, the calculation of CB is done by, let's consider this is your unbraced length. Remember very carefully, this is your unbraced length, not the entire length. So the bending moment diagram that you need to consider is the bending moment diagram under any particular unbraced length that you are monitoring or you are evaluating. Okay, this is LB, not the length of the beam. This is the unbraced length. Oops. And therefore, you must consider the bending moment diagram between a particular LB. Okay, be careful. And when you start considering the bending moment diagram under one unbraced length, what we do is we divide this into 4 equal lengths. Okay, that's L over 4, L over 4, LB over 4, and then LB over 4. And you can call that a quarter point. It's point A, point B, and point C. Okay. So now, when you divide the unbraced length into 4 equal lengths, you can now calculate what moment at each quarter point is. Okay, so we call that MA, MB, and MC. And once you have done that, you can calculate CB by using this formula. So let's look at the formula itself. Okay, that is the maximum moment in that range, in the range of that unbraced length, M max. And MA, MB, and MC are just moment at quarter point. Okay, so we have M max, any maximum value in that particular unbraced length, and then the moment at quarter points. Okay, and in this calculation, we use only absolute value, meaning if you have negative moment, you must use the absolute value and that it turns into the positive value. No negative value, just the absolute value. Okay, and please consider the coefficient. Let's say if you go back and look at the first case where your moment is constant, like this, you see every moment will become equal, right? If your moment diagram is constant. So let's say if every moment is equal, you can cancel every term out, and the coefficient on top or the numerator is 12.5. And for the bottom or the denominator is 2.5, 2.5 plus 3 plus 4 plus 3, which is also 12.5. So that means your CB will automatically become 1 if your moment is constant, okay, which is the worst case scenario. I can say worst case scenario constant moment will give CB equal to 1. And remember, this is the worst case scenario and CB is equal to 1. CB is meant to help reflect the fact that your bending moment diagram that is not constant can help, so for the lack of better word, strengthen the flexural capacity of your beam. Therefore, CB must always be greater than 1. Anyone who calculates CB and gets a value less than 1 and determines to use that, you will cause me to be very, very angry, so to speak. Okay, so CB reflects the fact that your bending moment is not constant, and it may help increase the flexural capacity of your beam. So it has to be greater than 1. The worst case scenario is that it is equal to 1. Okay, so let us take a quick look at some help from CB. Okay, we can begin with my case like this. Okay, so let's say if you have a simple beam without any brace point at all, and I have a point load here, that means my bending moment diagram will look like that. All right, and if I don't have any braces, it means that this is my LB. Okay, and let's say this point load is in the middle, and I know that the maximum value, point load in the middle, the moment is PL over 4. Okay, and we divide this into 4 equal lengths, and my MA will be at the quarter point, so that's my MA. My MB incidentally will be at the M max, and then I have my MC. So in this case, you see that my MA is equal to PL over 8. My MB is PL over 4. My MC is PL over 8. And my M max is PL over 4. Okay, so if I want to calculate the CB of this, because PL is just a typical term for every moment, so I can just use the coefficient of 1/8 and 1/4. Okay, so the CB for this case is going to be, for the numerator, 12.5 M max, which is PL over 4, so it's a quarter. And then divided by 2.5 M max, which is again PL over 4, so I use 1 over 4, plus 3 MA, MA is PL over 8, so it's 1/8, plus 4 MB, 1/4, plus 3 MC, which is 1/8. And I got 1.32. So you see 32% increase of the flexural strength. 32%. You think you're going to ignore that? Let's say if you have 1,000 baht in your wallet and somebody offers to increase the money in your wallet by 30%, would you take it? All right. Don't answer me. Let's move on to the second case where, let's say, it's the same beam, but this time I'm gonna create the scenario where it's just exactly like the case that I work. P here, but this time we have the brace in the middle. So LB becomes only half of the length, okay? So that means my bending moment diagram to calculate CB, in fact, you will need to consider, both regions of this beam, okay? The region on the left and the region on the right side of the point load, but they are identical. So it's safe to say that we can consider only one case. So that becomes the bending moment diagram under the unbraced length. Okay, and again, I divide this into 4 equal lengths. That's my point A, point B, and point C. So in this case, my MA is a quarter, and M max here is, that's PLO4 as well, right? So my MA is PL over 16. My MB is PL over 8. My MC is 3PL over 16. And my M max remains PL over 4. So that means my CB will be equal to 12.5 multiplied by M max, which is 1 over 4, divided by 2.5 M max, again 1 over 4, plus 3 MA, this time is 1/16. MB is 1/8 plus MC 3 over 16. Can you guess what this number is going to be? It is 1.67, or 67% increase of the moment capacity. So yes, that's true. I utilize this CB in the design of this beam. So I increase because of the fact that I have the bracing in the middle like this. And this is basically the bending moment diagram of the beam. Unbraced length is a half, and therefore this becomes the part where I calculate CB. And I did use CB equal to 1.67 in the design of this beam. That's why it is so small. Okay. You may go out and work in the real world and see many old school engineers always stay on the safe side and use CB equal to 1. That's because they don't talk to the structure. They don't understand the behavior of steel structure. And when you don't understand something, you become afraid. I've been saying this for many generations of you guys now, hoping that one day we can turn it over, because anywhere else in the world they use CB and the steel structure is small as it should be. If you want to use steel and you don't utilize what you have, it becomes very big and ugly and don't reflect the true strength of the material that you use. But again, you need to understand what you're doing. See, in this case, I am not afraid. I only tell them not to call me during the construction, and that's all. But no, it's just a joke. I'm not afraid. And because I put so many colors on it, you see that, maybe you can see from this beam. You see, it's a case where, you see, we have point load here. So yes, that means this beam also has the potential local failure as well that we talk about. And I did check that, and I found that this beam was more than capable of taking care of the point load. So no stiffeners were added, to the amazement of the contractor. Say, are you sure, Ajahn, are you sure you're going to do this? That yes, of course, I'm sure. And they were delighted because wow, they said they never quite met anyone who believed in the behavior of the structure. And so I wasn't afraid not to put anything unnecessary onto the structure. That's who I am, right? Otherwise, if you don't do what you teach, how can you teach? Right? So that's it, ladies and gentlemen. Before we have a break, let me show you another case. So this is a typical case where you may use your CB. Another case that you should know is just, let's say, a simple beam. Oops, change back to this. A simple beam with a uniform load. You know that your bending moment diagram is like this. It's not constant, okay? And I'm not going to show the calculation, but I can quickly tell you that, let's say if the unbraced length is equal to the length of the beam, even in this typical case, CB is equal to 1.14. We have 14% increase of strength, okay? Is there any question?
Teacher.
Yes.
How can I calculate when the bracing is not only one, if it has two?
Wait, let's say you have more than one bracing in one beam, right? That's your question.
Yes.
Good,
yes.
Very good. So let me draw you something. Let's say you have a beam. Okay. Loading doesn't matter. Say you have crazy loading going on. And then you have, say, bracing, 2 points. That enough? Okay. Oops. I think we have a problem. I think because the screen froze, so let me stop the share and do it again. Okay. Yeah, I know right away because the monitor doesn't change according to the iPad. So okay, let's say we have a simple beam, with loading condition doesn't matter, and we have 2 brace points. And from your loading condition, you analyze the beam, and this is your bending moment diagram. All right. Now, because you have 2 brace points, that means this beam will have 3 regions. Okay, this is your region 1, this is your region 2, and this is your region number 3. Now you need to investigate these 3 regions to see which one is your worst case scenario. And when you investigate your region number 1, this is your bending moment diagram, because this is your unbraced length number 1. Okay, so you divide this into 4 equal parts, so you get your MA, MB, and MC, and then M max. And then you move on to your second region, and then you investigate this with another LB, divide them into 4 equal points, calculate your CB, and go on. Okay, and then the third region, it's the same thing, right? Does that answer your question? Maybe I should have brought this up myself without you asking. It's a very good question. Thank you.
Okay, teacher. So it's same as if the bracing is not the middle.
Right, it can be anywhere. The bracing can be anywhere. You need to investigate the length between the bracings.
Okay.
Right? I can draw another case where it's more, say, severe. Let's say if this is your beam, and then this is one brace point here. Okay? Loading, we don't know. And then we have the bending moment diagram. Let's say this can be very small, and then, whoa, we have a big bending moment diagram here, right? And then that becomes your brace point. So I'm doing this so that you cannot guesstimate which is going to be your, more critical case. This is your LB, longer unbraced length with lower moment. So you can investigate your moment capacity here with CB calculated from this LB, and then another one here. Higher moment, but shorter unbraced length, like that. All right. Very good question. So we always have to investigate the unbraced length. And in one beam, let's say if you have 3 unbraced lengths, like the first case, you have to investigate all 3 of them before you can tell whether or not this beam is safe. And when you design the beam, again, you need to, because the unbraced length will become the issue with the flexural capacity of the beam as well. So when you know the unbraced length, you need to use my table C or 4 to pick up the beam size. Okay? Yeah, right. You know what? I don't have the design example for that. So maybe I'm going to need another, say, lab session to cover that so that, you guys don't miss out on anything. So is there any question? Or maybe, let's say if I can cover that today. Okay. Is there any question, folks? All quiet. So let me stop the share so that I can stop the record.